93 million miles away, something has just changed. A burst of energy tore free from the sun with the force of billions of hydrogen bombs, and right now, that disturbance is crossing the space between our star and Earth. Not over years or months, but within a matter of hours and days. Scientists have given the event a name that most people outside the space weather community will never hear: an X4.2 class solar flare. But the label is not the most important part. What matters is what this eruption may be carrying behind it, what it could still release, and how a civilization built around invisible electrical systems responds when the sun reminds us that it remains the most powerful force in our immediate cosmic neighborhood. This is the story of a storm that, according to the official forecast, is not expected to be especially dangerous. It is also the story of why that forecast may not tell the whole story yet. To understand the uncertainty, we first need to understand what the sun is actually doing. The sun is not the calm, unchanging disk many of us drew in school. It is a constantly moving ocean of plasma wrapped in a magnetic field so complex that even scientists who study it every day sometimes describe it simply as a mess. That magnetic field never stays still. It twists, stretches, folds back on itself, and becomes tangled like a garden hose left out in the heat. When the tension becomes too great, the field can suddenly rearrange itself. That process, known as magnetic reconnection, releases energy that may have been building for days or weeks in a matter of seconds. The visible result is a solar flare. The strongest flares can briefly outshine the rest of the sun in X-rays, even though they erupt from a relatively small region of its surface. Right now, one particular part of that surface has become the most active piece of real estate in the solar system. Scientists have identified it as sunspot group 43166, and over the past several weeks, it has produced powerful flares almost continuously. First came an X1 flare, followed by X1.8, X2.8, and X1.6 events. Then came the largest eruption in this sequence, an X4.2 flare classified as Earth-directed. That does not mean the flare randomly pointed toward us. It erupted while the active region was positioned almost directly in line with Earth. The letters in the flare classification system matter just as much as the numbers. TELS flares are relatively minor. M-class flares are stronger and can disrupt radio communications under the right conditions. X-class flares are the most powerful category, capable of affecting Earth's upper atmosphere and briefly interfering with high-frequency radio communication on the sunlit side of the planet. Each full step in the letter scale represents roughly 10 times more energy than the class below it. An X-class flare is not merely a little stronger than an M-class event. It represents an order of magnitude increase. And this region has now produced 5 X-class flares within only a few weeks, along with dozens of strong M-class flares. That is not the behavior of a quiet or fading sun. It is the behavior of a star in one of its most turbulent moods in years. But the flare itself is only the beginning of the story, because the real uncertainty involves what may or may not have been launched alongside it. Normally, a flare of this strength can be accompanied by something far more substantial, a coronal mass ejection, or CME. A CME is an enormous cloud of magnetized plasma containing billions of tons of solar material, hurled outward into space at speeds that can exceed 1 million miles per hour. If the flare is the flash of a gunshot, the CME is the bullet. The flash reaches Earth in about 8 minutes, because that is how long light takes to cross the distance between the sun and our planet. The CME, however, may take anywhere from 1 to 4 days to arrive. The unusual feature of this X4.2 flare is that it did not produce a clearly Earth-directed CME. The plasma erupted, but much of it appears to have remained near the sun instead of escaping directly into space. Scientists studying the active region believe the magnetic field above the sunspot may be unusually strong, effectively acting like a lid that holds much of the ejected material down. Flare after flare, energy builds beneath that magnetic structure, and flare after flare, the lid mostly holds. But the word mostly is doing a lot of work here. One eruption from the same active region, an enormous X8.1 flare among the strongest recorded during this solar cycle, did manage to break a CME free. It was not a perfect direct hit. Most of the material appears to be angled somewhat away from Earth's center, but models from US government space weather forecasters indicate that the outer part of the cloud may begin brushing Earth's magnetic field within the next day, with the densest material arriving roughly a day later. That CME is not moving especially fast by solar standards. Its speed is estimated at around 400 kilometers per second, which is relatively modest compared with the fastest eruptions. Based on that speed and its trajectory, the official forecast calls for a G1, or minor, geomagnetic storm. G1 is the lowest level on a 5-step scale that rises to G5. the category associated with historic storms capable of producing severe technological disruption. This event is not expected to resemble the Carrington event of 1859, which set telegraph offices on fire and produced auroras as far south as the Caribbean. No serious forecaster is suggesting that, but the official forecast is only a snapshot, based on the information available at the moment. And when it comes to space weather, the information available at the moment is not always complete. That is where an independent spacecraft is beginning to change the picture. The spacecraft providing that additional clue is Solar Orbiter. It is positioned almost directly between the Sun and Earth, although far enough to one side that it can sample the incoming solar wind slightly before the disturbance reaches us. During the past day, Solar Orbiter detected a sharp shock. Its onboard magnetometer recorded the magnetic field jumping from approximately 17 nanotslas to 33 nanotslas in a short burst, an increase of roughly 15 nanotslas within moments. That is not a subtle reading. It is the signature of a spacecraft being physically struck by something moving through space. Something is coming. The real questions are how hard it will hit and whether anything else is following behind it. Forecasters tracking this active region have pointed to another important detail. Even when a flare does not launch a clean, obvious CME toward Earth, repeated eruptions can still disturb the solar wind. Instead of thinking about one isolated wave, imagine a stretch of rough ocean. The confirmed CME may be the main wave, but repeated flaring can create turbulence around it, making the solar wind more disturbed and unpredictable during the same period. Because of that background activity, several forecasters now believe the storm could be stronger than the official minor rating suggests. Some have raised the possibility of G2 or even G3 conditions. A G2 storm is moderate, while G3 is considered strong. Either level could push the Aurora Borealis much farther from the poles than usual and generate measurable electrical currents in long-distance power transmission lines. There is also a second possibility that makes this event more difficult to evaluate. Remember the magnetic lid that appears to be holding back much of the active region's plasma. That lid is still present. Sunspot group 43166 has continued to grow physically larger, even though its internal magnetic complexity has eased slightly. More importantly, it remains inside what forecasters call Earth's strike zone, the central portion of the visible solar disk from which an eruption is most likely to travel directly toward our planet. The region is expected to remain in that position for roughly another day and a half before rotating toward the edge of the Sun as seen from Earth. That timing matters. The fact that a major CME has not yet escaped from the region does not mean the plasma is gone. It may mean the material is still trapped. Every additional X-class flare from this area could represent another crack forming in the magnetic lid. If that containment fails while the active region is still facing Earth, the result would not be another minor storm. It could be a major eruption aimed almost directly at us, arriving while the solar wind is already unsettled, and while Earth's magnetosphere may still be processing the first disturbance. Forecasters are not predicting a Carrington-level catastrophe. Events that extreme remain rare, perhaps occurring only once or twice in recorded history. But the distance between a minor storm that produces attractive auroras and a strong storm that creates real infrastructure stress is precisely where this event currently sits. That gap explains why space weather forecasters, who are usually cautious and understated, are watching this situation more closely than they have watched most events in recent months. The forecast may say G1, but the conditions surrounding that rating are more complicated than the number suggests. So what does a geomagnetic storm actually do once it reaches Earth? At the gentler end of the scale, especially during G1 and G2 conditions, the most noticeable effect is also the most beautiful. Charged particles from the solar wind follow Earth's magnetic field lines toward the polar regions. When those particles collide with oxygen and nitrogen molecules in the upper atmosphere, the gases glow. That glow is the aurora. Under normal conditions, the aurora remains concentrated in a narrow ring around the Arctic and Antarctic. During a geomagnetic storm, however, that ring expands. A moderate storm can push the northern lights into the northern United States, southern Canada, Scandinavia, and other parts of northern Europe. For skywatchers, that is the reward. It is why photographers travel to high-latitude locations during periods of solar activity, cameras prepared, and waiting for the forecast to come true. But the same particles that create the lights can also cause quieter forms of disruption. Geomagnetic storms induce electrical currents in long, conductive systems such as power lines, pipelines, and railway signaling networks. During a stronger event, those currents can place additional stress on transformers and sometimes trigger protective shutdowns. Satellites can experience increased drag when the upper atmosphere heats and expands, subtly changing their orbits. GPS accuracy can deteriorate for hours, and high-frequency radio systems used by aviation and maritime operations may experience blackouts or interference. At G1 through G3 levels, none of these effects is expected to create a society-wide blackout. That kind of outcome belongs to the rare extreme end of the scale. But not catastrophic does not mean nothing. It means the storm occupies the space between a beautiful light show and a genuine technological warning. Modern life depends on systems that can be affected by even moderate geomagnetic activity. Airlines operating polar routes between North America and Asia may reroute flights farther south during strong storms, both to reduce communication problems near the poles and to limit radiation exposure for crews on long, high-latitude journeys. Farmers using GPS-guided tractors for precision planting may see their positioning drift by feet instead of inches. Oil and gas companies monitoring pipelines watch for induced currents that can accelerate corrosion over time. None of these effects is necessarily an emergency on its own, but they represent the kind of small, distributed friction that accumulates across an economy quietly built around reliable satellite signals, stable communications, and a calm space environment. The sun does not need to destroy the power grid to create problems. It only needs to make thousands of interconnected systems perform slightly worse at the same time. That is why utility companies and satellite operators do not treat space weather forecasts as background noise. Grid operators in regions with a history of geomagnetic sensitivity, including Canada, the northern United States, and Scandinavia, can take preventive measures when a stronger storm is expected. They may adjust transformer loads, bring reserve capacity online, or change the way electricity moves through the network. Satellite operators can place spacecraft into safe modes and temporarily shut down non-essential systems to reduce the risk from radiation spikes or atmospheric drag. Most of these actions never make the news. That is exactly the point. The difference between we saw this coming and we did not often matters more than the storm's numerical rating alone. Earth has endured far more powerful solar storms than the one currently approaching, and history is the reason scientists are paying attention without panicking. In September 1859, British astronomer Richard Carrington observed an extraordinarily bright flash erupt from a sunspot. Less than a day later, the resulting geomagnetic storm became so intense that telegraph operators across Europe and North America reported sparks leaping from their equipment. Some telegraph machines caught fire. Others continued sending messages even after operators disconnected them from their batteries, powered entirely by currents induced in the wires. Auroras appeared as far south as Cuba and Hawaii, and they were bright enough that some witnesses claimed they could read newspapers under the light at midnight. That event, now known as the Carrington event, remains the benchmark against which later solar storms are measured. The current event falls dramatically short of that level. More recently, in March 1989, a powerful geomagnetic storm induced currents strong enough to trip protective relays in Quebec's power grid. The entire province lost power for approximately 9 hours, affecting millions of people during a Canadian winter. In 2003, a series of storms known as the Halloween storms damaged satellites, disrupted airline navigation and communications, and caused a brief power outage in Sweden. These historical examples help forecasters understand what a G2 or G3 storm could realistically mean for a technologically dependent society. The event unfolding now remains well below those thresholds for the moment. But the reason forecasters continue watching is not only what has already happened. It is the fact that the source region has not finished producing energy. Perhaps the most important lesson from this event has little to do with one flare or one sunspot group. It is about timing. The sun operates through an approximately 11-year cycle of rising and falling activity, and current evidence suggests we are near or just past the peak of the present cycle. Scientists call that period solar maximum. During solar maximum, sunspot groups become more common, more complex, and more likely to produce rapid sequences of major flares. In a very real sense, we are living through the loud part of the solar cycle. That has consequences far beyond aurora photography. Modern civilization depends on technologies that did not exist during previous periods of strong solar activity. Global positioning systems, satellite-guided agriculture, aviation networks, financial transactions timed through satellite signals, and a power grid that is more connected, automated, and in some areas older than ever before. Space weather forecasters working at agencies, most people have never heard of monitor the sun around the clock because our dependence on vulnerable technology has grown alongside the technology itself. This is not a reason for alarm. It is a reason for steady, competent monitoring, much like meteorologists track hurricanes. They watch the system, update the forecast as new data arrives, and acknowledge when uncertainty remains. As of now, the official forecast still reads G1 minor. The confirmed CME is expected to arrive within the coming day, with the densest part of the plasma following approximately a day later. Skywatchers across Northern Europe and North America are being told to expect a good, and possibly very good, opportunity for aurora. But underneath that modest rating is a far more complicated picture. An active region continues producing major flares without fully releasing the energy building beneath its magnetic field. Independent spacecraft data has already detected a genuine shock moving through the solar wind, and the active region remains inside the strike zone, aimed almost directly at Earth for at least another day. Those three facts are why the event deserves more attention than a routine G1 forecast would normally receive. Somewhere above us tonight, the story is still being written. It is not being written by people on Earth, but by a star 93 million miles away that has just demonstrated how small the distance can feel when solar activity begins moving in our direction. To see why the official forecast could still change, it helps to examine the timing of the incoming material. A solar flare announces that magnetic energy has been released. A CME determines whether that release becomes a significant geomagnetic event here on Earth. The flare's X-rays arrived within minutes, potentially affecting radio systems on the sunlit side of the planet. The CME travels much more slowly, giving forecasters a period of 1 to 4 days to examine its speed, direction, structure, and magnetic orientation. But those measurements are never perfect at the moment of launch. A CME may appear to be aimed away from Earth while its outer edge still clips our magnetic field. A cloud that looks weak from a distance may contain a particularly strong southward magnetic component. And a sequence of eruptions can disturb the solar wind around the main CME, creating conditions that are more turbulent than a simple model predicts. The most important factor once the CME reaches Earth is the direction of its magnetic field. Earth has its own magnetic field, and the way the incoming CME field aligns with it determines how efficiently energy can enter the magnetosphere. A strongly southward magnetic field is especially effective because it points opposite to Earth's field, allowing reconnection and transferring energy into near-Earth space. A northward field generally couples less efficiently, reducing the storm's strength even if the CME itself is substantial. That is one reason the official forecast can only provide a range. The CME's speed and broad trajectory may be estimated days in advance, but its critical north-south magnetic orientation is often unknown until shortly before arrival. Spacecraft positioned near the L1 Lagrange point, including DSCOVR, serve as the final warning system. They sample the solar wind roughly 15 to 60 minutes before it reaches Earth, giving operators a narrow but valuable window to respond. During that interval, grid operators can make final decisions about switching and transformer loading. Satellite operators can adjust spacecraft attitudes or activate protective modes. Radio operators at high latitudes can prepare for propagation problems, and Aurora watchers can check whether the sky is clear at the moment the storm begins. For people hoping to see the Aurora, the forecast is promising but conditional. A G1 storm would mostly keep the northern lights near Canada, Scandinavia, and other high-latitude regions. G2 conditions could push the display into the northern tier of US states and across more of northern Europe. A G3 storm might expand the visible aurora toward the mid-Atlantic states, including areas near New York and Washington, D.C., while on the European side it could reach latitudes comparable to Paris and southern Germany. Those are credible possibilities, not guarantees. Local cloud cover, light pollution, the exact strength of the storm, and the timing of its peak relative to local darkness all matter. The aurora may be intense above a location, but invisible from the ground because clouds block the view. A strong storm may peak during daylight in one region and produce a spectacular display elsewhere several hours later. The KP index is one of the main indicators observers can follow. It is updated approximately every 3 hours using measurements from a global network of ground magnetometers. KP5 corresponds roughly to G1 conditions, with aurora primarily visible in Canada and Scandinavia. KP6 corresponds to G2 and expands the auroral oval into the northern United States. KP7 corresponds to G3 and can push the display toward the mid-Atlantic states, France, and southern Germany. Each step represents a real geographic expansion, not merely a change in a number. During a compound or particularly disturbed solar wind event, KP can rise from 5 to 7 within a few hours as the storm's main phase develops. That rapid movement is one reason observers should not assume that an early, quiet sky means the night is over. The most dramatic conditions may arrive later, after the first shock has passed. For infrastructure operators, the aurora is only the visible surface of a much larger process. The same energy that causes atmospheric gases to glow can drive currents through power systems, increase drag on satellites in low Earth orbit, reduce GPS accuracy, and disrupt high-frequency radio communications. At G3 levels, all of those effects can occur at the same time. The aurora is the part of the storm that makes people look up. The other effects are why power grid operators in places such as Quebec, satellite teams responsible for spacecraft in orbit, and radio operators supporting aviation and maritime activity take the forecast seriously. Their work is not based on fear of a guaranteed disaster. It is based on reducing avoidable risk while the sun is active. The current event also illustrates why solar maximum deserves attention. During the active phase of the sun's 11-year cycle, complex sunspot groups appear more often and have a greater chance of producing powerful flares and CMEs. That does not mean every flare becomes dangerous, and it does not mean Earth is constantly at risk. It means the background probability of significant events is higher, making continuous monitoring more important. Our technological dependence has changed the consequences of solar activity. A century ago, a geomagnetic storm might have disrupted telegraph systems and compasses. Today, the same broad category of disturbance can affect satellite navigation, precision agriculture, flight routes, communications, timing systems, and interconnected power networks. Most storms still produce manageable effects, but the number of systems exposed to even small errors has grown dramatically. That is why agencies track the sun with spacecraft, ground observatories, coronagraphs, magnetometers, and solar wind monitors. They are building a chain of information that begins with a flare on the solar surface and ends with measurements taken just before the disturbance reaches Earth. Every step narrows the uncertainty, but none removes it completely. As of now, the confirmed CME is still expected to produce a minor geomagnetic storm. The strongest material should reach Earth roughly a day after the first effects begin. The official outlook suggests that Northern Europe and North America may experience a good aurora opportunity if the timing, darkness, and cloud cover cooperate. But three details continue to complicate the forecast. First, the active region has produced a series of major flares rather than a single isolated event. Second, Solar Orbiter has detected a sharp shock in the solar wind, confirming that an organized disturbance is already moving through space. Third, the sunspot group remains aimed toward Earth and may continue producing eruptions before it rotates away from the direct line of fire. That final detail is the most important. A region can be powerful without being dangerous to Earth if it is positioned on the far side of the sun or near the edge of the visible disk. But when it sits near the center of the Earth-facing hemisphere, even a moderate CME has a better chance of arriving here. Sunspot group 43166 remains in that geo-effective position for at least another day, which means the forecast cannot simply focus on the CME already in transit. Another eruption from the region could create a new problem. If the magnetic lid above the sunspot weakens, a later X-class flare might release a much more direct and substantial CME. That new cloud would not arrive immediately. It would still require time to travel across space, but it could follow the first disturbance, creating a sequence rather than one isolated event. A magnetosphere already unsettled by the initial CME would have less time to recover before the next wave arrived. This does not mean a major eruption is guaranteed. It means the possibility remains physically credible while the active region is still facing Earth. Forecasting solar storms requires separating what is observed from what is merely possible. The observed facts are clear. The region is active, several powerful flares have occurred, one confirmed CME is moving toward Earth, and a spacecraft has measured a shock in the solar wind. The uncertain part is how strongly the incoming magnetic field will couple with Earth and whether the sun will launch another significant eruption before the geometry changes. That distinction is important because space weather headlines often leap from possibility to certainty. A potential G3 storm is not the same as a confirmed G3 storm. A possible CME is not the same as a direct hit. Scientists are watching because the upper end of the forecast matters, not because the worst outcome is expected. For now, the most reasonable description is that Earth faces a potentially active but still manageable solar weather episode. It may produce widespread aurora and minor technological effects. It may become stronger if the incoming magnetic field turns sharply southward. Or it may remain close to the official G1 forecast if the field orientation is unfavorable for energy transfer. The central question will be answered when the CME reaches the solar wind monitors near the L1 point. DSCOVR and similar instruments will measure the magnetic field strength, the solar wind speed, the particle density, and most importantly, the BZ component. If BZ turns strongly southward and remains there, Earth's magnetosphere will absorb energy efficiently and the storm could move toward G2 or G3 conditions. If BZ remains northward or fluctuates frequently, the coupling will be weaker and the event will likely stay closer to the lower end of the forecast. That one measurement will determine more than the color of the aurora. It will influence how far south the auroral oval expands, how much stress is placed on long-distance power lines, how much satellite drag increases, how accurately GPS systems perform, and how severely high-frequency radio links are disrupted. It is a reminder that space weather is not a single event with a single outcome. It is a chain of interactions, and the orientation of one invisible magnetic field can change the result. For skywatchers, the best opportunity may come 12 to 24 hours after the first CME shock reaches Earth, when the main phase of the geomagnetic storm develops. The exact timing will vary, but the initial arrival does not always produce the strongest aurora immediately. The magnetosphere may need time to absorb and redistribute the incoming energy before the auroral oval expands to its greatest extent. That means observers should watch the forecast through the entire window rather than checking once and giving up. A location may have clouds during the first alert and clear skies during the storm's strongest phase. Another area may have a clear sky but daylight at the wrong moment. Light pollution can hide weaker displays, while a dark location can reveal aurora that would be invisible from a city. At the same time, the sunspot group itself remains a continuing source of uncertainty. As it rotates toward the edge of the visible disk, its eruptions will gradually become less likely to strike Earth directly. But until that geometry changes, the active region can still launch another flare or CME aimed our way. The magnetic lid may continue holding, or it may finally fail more completely. Scientists cannot determine that outcome in advance with certainty because the solar magnetic field is constantly evolving beneath the surface. This is what makes the current storm different from a simple, neatly defined forecast. The approaching CME is one story, but the active region is another. The first may produce a minor storm. The second could determine whether the event ends there or becomes part of a longer sequence. Meanwhile, the surrounding solar wind may already be turbulent because of the region's repeated eruptions, adding another layer of complexity to the forecast. There is no credible reason to expect a Carrington-level catastrophe from the event currently being tracked. The available observations do not support that conclusion. But the fact that the storm is not expected to be catastrophic should not lead us to dismiss it. A G1 to G3 event can still create aurora at unusually low latitudes, cause temporary radio and GPS problems, increase satellite drag, and force operators to make precautionary adjustments. The larger lesson is that modern civilization is living through a period of elevated solar activity while depending more heavily than ever on technology vulnerable to the space environment. That is not a reason to panic. It is a reason to understand the forecast, follow reliable updates, and recognize that uncertainty is a normal part of space weather science. As of now, the official forecast remains G1 minor. The confirmed CME is expected to begin affecting Earth within the coming day, with the densest material following approximately a day later. Northern Europe and North America may see a strong aurora opportunity if the storm reaches the upper end of the forecast and local conditions cooperate. But beneath that modest official rating is a more complicated reality. A highly active sunspot group, repeated X-class flares, a confirmed CME, a shock already detected by spacecraft, and a magnetic region still aimed almost directly at Earth. Somewhere above us, that story is still unfolding. It is being shaped by magnetic fields we cannot see, particles moving through space, and a star whose activity can change the conditions around Earth without warning. The sun has just reminded an entire planet how small the distance between a quiet sky and a geomagnetic storm can really be. The next measurements will tell us whether this event remains a minor display, grows into a stronger storm, or reveals another eruption waiting behind the first. Watch the solar wind data, follow updates from space weather agencies, and keep an eye on the skies if you live beneath the possible auroral zone. The storm racing toward Earth may still surprise us.